In this lesson, I'd like to go over the definition of complex numbers and then do some computations with them as well. So to start with, we need to define something called the imaginary unit, and that is the square root of -1. So you can't actually take the square root of -1 and talk about a real number, so in this case we just define it to be something called I. So I've written that down here. You could also define it as I squared equals -1, and this is basically taking this equation and squaring both sides. So let's see where this shows up. So in example 1, I have a couple of equations written here that I'd like to solve by using a guess and check method. So we've already done this one before. X squared is equal to 9, but by guess and check, you can say, oh, I know the two solutions. 3, because if you square 3, you get 9. But also, if you were to square -3, the negative cancels, 3 squared is 9, so those are your two solutions, -3 and +3, or simply plus or minus 3. What if we try this approach over here? I know there's no real solution. Any real number that you square is either 0 or positive, so it could never take on a negative value. But this is where complex numbers come into play. What I'm going to do is plug in something involving I for x and verify that this equation is true. Okay, so I'm guessing the answer. I know it has to have a 3 because that's how, if you square it, you'll go to 9. But I'm also going to put an I in here. 3i is actually in the parentheses because the I will give me the negative back. When you square this, you square 3, but you also square I. 3 squared is 9. We defined I squared to be -1, and the product of those two numbers is -9. Therefore, 3i is a solution. Are there any others? And the answer is yes. You can still use 3i and square it, but then you can also put a -1 in front of the whole thing as well. That is, you're squaring -1, you're squaring 3, and you're squaring I. This time the negative in front just simply goes away. 3 squared is 9, I squared is -1, the product of all of this is -9, so we do in fact get this second solution. This equation has two solutions as well. You get that x is equal to 3i and also -3i, or simply you could just write it again as plus or minus 3i. Now that we have defined the imaginary unit I, we can completely define something called a complex number. They are any number of the form a plus b times I, where a is called the real part and b is called the imaginary part. So maybe just to write out a couple of examples, it's pretty simple to do. You have, let's say, the number 1. Maybe you have the number 5i. If you add those two together, you can't combine them because they're not like terms, but this is what we call a complex number. It has a real part and it has an imaginary part. It could be that your real part is 0, so 0 plus 3i, or simply 3i, is a complex number. So maybe just a couple of others, maybe something like, 0.5 minus 1.6i, or how about 1/2 plus the square root of 2i. Those are two more examples. And just one other quick definition here. If you change the sign between the real and the imaginary part, we call that number the complex conjugate of the number a plus bi. So next to each of these numbers, I'm just going to replace the number itself with its complex conjugate. Like this one here, 1 minus 5i is its complex conjugate. Here, since it's a plus 3i, we get minus 3i. This one we're just going backwards. It's going to be 0.5. It'll go to plus 1.6i. And this one here is going to be 1/2 minus the square root of 2i. So those things being defined, let's check out example 2, where we're basically going to take complex numbers and we're going to add, subtract, and multiply them just to see what that looks like. Starting with this one, 2 plus 3i plus 6 plus 8i. To add these two together, we will treat the 2 and the 6 as like terms, the 3i and the 8i as like terms, and simply add those two together. This first one is going to be 2 plus 6 plus 3i plus 8i. I'm combining the similar terms together. This gives us 8 and 11i, and that's how you can add two complex numbers together. Here, if we try that over here with 5 plus 2i plus 5 minus 2i, notice that this number here is a complex number, and this one is its complex conjugate because they differ from a plus to a minus and in no other way. Let's see what happens if we add a complex number with its complex conjugate. This is going to be 5 plus 5, then it's going to be plus 2i minus 2i. And the result is 10 plus 0i, or simply you could just say 10. So it's interesting that when you add a complex number with its conjugate, it becomes a real number. All right, let's go down to this example. Now we're subtracting two complex numbers. So basically we're just going to distribute this negative into the parentheses, so that negative 1 is going to go to the 3 and the negative 10i, but everything else works the exact same way. This is going to be negative 7 plus 6i plus negative 3 plus 10i. Okay, so that means we're combining the negative 7 and the negative 3, as well as the 6i and the 10i, giving us a final answer of negative 10 plus 16i. We can't combine any further, that's a complex number. And for this last one, okay, now we're not adding or subtracting, but we're multiplying two complex numbers together. And notice that this one here actually is what happens if you multiply a complex number with its conjugate. So to do this, we just have to use the distributive property where 5 first gets multiplied into both terms, and then this 2i gets multiplied into both terms. Let's write that out. If you first distribute the 5, we get 5 times 5, which is 25. Then we get 5 times negative 2i, that's minus 10i. If we then multiply in the 2i, we get a positive 10i, and then a minus, so it's going to be 2i times negative 2i, so it's going to be negative 2 times 2 is 4, and I times I is I squared. A little bit more complicated, but let's just carefully combine like terms and move forward. Let's see, well, we got 25. I'm not sure what to do with that yet. I have a negative 10i and a plus 10i, which is 0. I won't write it, but I do have this minus 4i squared at the end. And actually, we defined I squared to be equal to negative 1. So what I'm going to do is replace I squared with negative 1. I get that this is really 25. That's minus a negative 4. That's plus 4. And my final answer is 29. The complex conjugate is an important definition because of what happens in these two examples here. If you add them, it just becomes a real number. And if you multiply them, it becomes a real number as well. Given complex numbers, we can add them, subtract them, and multiply them without too much trouble. But what about dividing two complex numbers? So let's say 4 plus 2i divided by 5 plus 2i. What happens if we try to do that? If I write this out as a fraction, this is 4 plus 2i divided by 5 plus 2i. And I'm kind of stuck because I don't really know where to go at this point. So essentially in this example, I'm going to show you a trick for dividing two complex numbers. And here's the trick. We're going to multiply this thing by 1, which doesn't do anything. But my second step is going to be to write 1 in a more convenient way. I'm going to leave the first fraction alone, and I'm going to write 1 as a fraction where I have the same thing in the numerator as the denominator, which is the same thing as saying you're multiplying by 1. And the thing I'm going to multiply by is the complex conjugate of 5 plus 2i. I'm going to place that right here. which means I therefore have to put it in the numerator as well. The reason I'm doing this is because when I multiply the denominators, I know it's going to become a real number. So let's check it out. All right, so here I've definitely multiplied by 1. It's just a very complicated way to write 1. Now I can simply multiply the numerators and multiply the denominators. Let's do that work separately off to the side. Let's start with the numerator. What is 4 plus 2i times 5 minus 2i? I want to be careful here. I first multiply in the 4. I then multiply in the 2i. Here's what I get. 4 times 5 is 20. 4 times negative 2i is negative 8i. When I multiply in the 2i, I get 10i minus 4i squared. If I simplify this, I get 20. I get plus 2i. Check this out though. I have 4 and I squared. I squared is negative 1, which makes this a positive 4. I saw this in the previous example, so I'm just going to put plus 4 at the end. Again, that's coming from this I squared. It's equal to negative 1, which changes this minus to a plus. So the final answer here is I can combine the 20 and the 4 to 24, but then I also have 2i. That's what happens when I multiply the numerators. Let's now multiply the denominators. That is, I want to multiply 5 plus 2i and 5 minus 2i. I'm going to write this one out again. But just to go over it, again, you're multiplying the 5 in and also the 2i. It should be that the imaginary part cancels. Let's see if that happens. Okay, I get 5 times 5, and that is 25. I get 5 times negative 2i, that's negative 10i. I then distribute in the 2i, so I get a positive 10i, that's great. And then I get minus 4i squared. Again, that thing at the end is going to become plus 4. So if I write my next line out, I get 25. The 10 i's cancel because one's positive, one's negative. I get a plus 4 at the end, and just like we saw last time, that's 29. Let's take all this work we did and go back up to the original problem. When I multiply the numerators, that's what I did here. I'm just going to place this result in its place. That is, the numerator multiplies to 24 plus 2i. And that's divided by whatever I get for the denominator, which was all of this work we did here, and the answer was 29. Since 29 is being divided into the entire numerator, it's really being divided to both terms. You can break this up into two separate fractions. That's 24 over 29 plus 2 over 29i. This is quite a lengthy process. I wanted to at least check out one example of this. It's tricky because it involves this idea of multiplying by 1, but using the complex conjugate to make the denominator become a real number. But the second it is, you can split this thing into two fractions, and you have your final answer, which I have here. And we'll end this lesson with a final warning, and that is for dealing with square roots where you have products. We use this idea a lot in real numbers, where if you have the square root of two numbers that are being multiplied, you can break it up into the square root of two pieces separately. Unfortunately, this is only valid if a and b are not both negative. So if you're talking about complex numbers, you have to be careful when using this here. To see what I mean, I wrote the same example down twice, but I'm going to solve it in two different ways. The first way I'm going to solve it is by first multiplying negative 4 and negative 9, and then taking the square root of the result. So that is up here. If you're following like an order of operation, you would say negative 4 times negative 9 becomes positive. It's positive 36, and we define the square root to be 6. So it's very easy to get your answer that way. But let's say you took the approach of splitting this up into two separate square roots. That would be you first look at the square root of -4 and then the square root of -9. This formula, it's valid for real numbers. Does it work for complex numbers too? Let's see. Okay, the square root of -4 is going to be 2, and then you have the square root of -1, which is I. If you do the same thing for the square root of 9, okay, the square root of 9 is 3, and the square root of -1 is I. It would have to be this. When I multiply everything together, 2 times 3 is 6, and I times I is I squared. And we've seen this a few times now, but if you square I, you get -1. And this gives me a final answer of -6. And here is the problem. This can't happen. These are, you get 6, but one's positive and one is negative. The fact that this happens with these two different approaches means that we unfortunately cannot use this up here. What goes wrong is if you have two negative numbers under the square root. In any other situation, this rule is fine, but I just put this here as a warning to be careful when we simplify using negative numbers and square roots.